So hello to everyone. First of all, it's a great pleasure to be among all of you today. My name is Fatlinda Avdullai, a PhD student at TU Kaiserslautern. Today my talk will be about modeling time series with trend and seasonality in the focus about learning capabilities of artificial neural networks. This is a joint work with Professor Ralph Korn. Basically, I will go through motivation, modeling time series with trend and seasonality, using traditional forecasting models and new approaches with respect to artificial neural networks. As a case study, later we will given to forecast some real data sets from the private health insurance sector and some conclusion. Basically, the motivation about this research is that modeling the time series with trend and seasonality has been main research for a long time. Therefore, there will be given some estimation of the trend and seasonal components using both the traditional forecasting models and new approaches with respect to artificial neural network. Furthermore, we'll focus on some limitations of the neural networks in learning the trend and seasonal components. Therefore, we will be given later on some current approaches which are used to estimate the time series components with respect to artificial neural network. And as a case study, we will be use the real data set to predict the triggering factor in private health insurance company by using a special tariff. But in this case, we will be using the neural networks and hybrid approaches to forecast the triggering factor. Modeling time series with trend and seasonality. Basically, the data that we have taken and models that we have considered were based on time series. And a time series is just a variable which is measured sequentially in time over at a fixed interval known as a sampling interval. Then the resulted data form the time series. And the main features of many time series are the trend and seasonality. The trend occurs when we have a long-term increase or decrease in the data, while the seasonality is when the data actually are affected by the seasonal factors, such as, for example, the day of the week. And mainly the researchers have tried to model those components by giving different models, decomposition methods, and the simplest one and some classical decomposition that are quite known is the additive decomposition, where the data Y are decomposed as a sum of the trend T, seasonality S, and the residuals in the series. And any forecasting models tries kind of to estimate all three models and give good forecasting accuracy. Another decomposition is the multiplicative decomposition, which is just the product of each of them. Among traditional forecasting models that have been used to estimate and model the time series with trend and seasonality is the regression model that kind of tries to explain the relationship between some dependent variable and independent variable. A model that explains or includes the seasonality and trend is this model, where the seasonal model containing S season and trend T is given by this formula, where particularly the trend is estimated following this term, while the seasonality with S season, giving delta S at time T as a dummy variable, estimates or model the seasonality in the time in the series. If someone tries to use this regression model, then a model building strategy should be followed, such that parameters are estimated usually by the linear least squares method. Then the predictor are selected by using some information criteria such as corrected AIC, and later the residuals are analyzed to check the assumptions of the model. Instead of using the regression model, because those are quite relevant or important when trend and seasonality are deterministic, but however, when we occur to be that the seasonality and trend are stochastic, there are also powerful forecasting models that are based on Box-Jenkins method. Those try to estimate or to explain the correlation in the data. The well-known method from the Box-Jenkins method that estimates the seasonality and trend is the non-stationary seasonal ARIMA model, where the ARIMA model stands for the autoregressive integrated moving average, which is just a combination between the past forecast error and the past lag value of the same observation. So the ARIMA model has a parameter PDQ, which kind of estimates and models the non-seasonal part of the model by adding the upper parameters PTQ with S standing for the seasonal period, tries to model and estimate the seasonal part of the model. Of course, this model is represented by this formula. So the ARIMA model with those parameters is represented by this formula with B standing for the backshift operator. So it's kind of, as I said, it's a kind of a combination of the past lags of the same observation and the past forecast error. However, in dynamic, for example, regression models cannot handle the dynamics in the time series that, for example, data can have, and the ARIMA model can kind of handle, or vice versa. The ARIMA model cannot have other independent variables or other information in the model. It only has the lagged past values, or has only the past forecast error. And the researchers in this case have introduced another model, so the dynamic regression models, that combines both of them. So it combines the regression part and the ARIMA model. The regression part is here with K predictors. So our data suppose has K predictors, so some independent variables that are relevant for our data, and now eta t is the error in the series which is correlated, and this correlation is explained by the ARIMA model. Alternatively, there has been a lot of decomposition method that has been developed from a long time ago, starting from 1920s, because time series and the components are quite important, and estimating them, it means that you will have, so estimating and modeling them with a good method, you will have a good forecasting so good forecasting accuracy in the end. And one of the simplest decomposition method is the moving average, which is kind of, for example, the trend T is just as a sum of, so using the same observation with some order M. Alternatively, there is also some other decomposition method or methods that estimate the seasonality, such as the Fourier series, that combines the sinus and cosinus terms to estimate the seasonality. While powerful methods or powerful decomposition method that are introduced recently is the one that is based on X11 method, which actually uses the linear filters to estimate the trend in seasonality. And this X11 method is further enhanced to X13 ARIMA seeds, which gives the researchers to the idea or the chance to estimate the trend in seasonality by using the linear filters or by using some ARIMA decomposition. Such a decomposition method is available in many programming languages, and it's quite easy to use as well in order to estimate those components. Alternatively, neural network models or artificial neural network models are being successfully applied in many fields of business, industry, and science. Of course, the attractiveness of the neural network is that they are data-driven and self-adaptive, meaning that they need only some basic modeling framework. Moreover, they are universal approximators. This universal approximators, meaning that it can approximate any function to any desired accuracy. And another important factor is that they are non-linear model. So compared to the traditional ones, so compared to regression and ARIMA model, those tend to be linear model, and the neural network is in this case non-linear, which kind of for the data or for the time series is really good because may explain the nonlinearity in the data. Although many types of neural network models have been proposed for forecasting, the most known method is the feed-forward neural network. with only one hidden layer. Basically, what I was saying is that the feed-forward neural network are kind of formed with a number of interconnected nodes which are found into the layers, and those are known as neurons. And for completeness, I will just show you a simple one hidden layer feed-forward neural network, where in the input layer we have the input variables or the information about the data. In this case, we have the past lagged value of the same observation, and in the output layer we have the forecast value y. The hidden layer with some appropriate hidden layer and some weights. So the appropriate activation function and some hidden weights will transform the data into a proper value for the output layer. Such a network is shown with this formula, where the future value y of t is given with, so this framework is given with this formula, where omega I and omega ij are the model parameters. P is the number of input nodes, Q is the number of hidden nodes, and sigma is the activation function, which represents the nonlinearity in the neural network model. However, a part of the advantages of using neural network, there has been a debate concerning the learning capabilities of neural network to model time series with seasonality and trend. There does not exist, any consensus on how to select a relevant set of input variables and legs for neural networks given time series components. Furthermore, it's still always the question, should we preprocess the time series or not? Meaning that, should we remove the trend and seasonality prior to neural network modeling? Most of the researchers conclude that deseasonalization and detrending, so removing the trend and seasonality from the data, will increase the forecast accuracy when the neural network are applied as a forecasting method. Furthermore, according to the researchers, this will as well decrease the kind of the modeling framework in terms of how many input variables should we include in our model, and how many hidden nodes will be required to estimate such trend and seasonality. And removing the trend and seasonality from the time series will make more a simple method for the neural network, and therefore parsimonious. For example, in the paper of Peter Zhang and Min Ji, neural network forecasting for seasonal and trend time series, they investigate how to best model these components. In their empirical results, they have shown that deseasonalizing and trending the data is better for the neural network, and therefore increases the forecast accuracy. And the reason behind this is that the seasonal fluctuations may dominate the remaining variation in the series. Why? Because most of the time people should put attention to the part that it's unknown in the series. A seasonality most of the time is the same. Someone can take the past values from some estimation made on the earlier years, depending, of course, what kind of data you have. And therefore, neural networks should focus on the other part in the series and tries to estimate that part as well. While an explanation for why the trend should be removed is that the trend time series do not meet the conditions for universal approximation, meaning that using, for example, the activation function such as the sigmoid function being a bounded function for the trend component, most of the time, not most of the time, but the trend component is estimated by an unbounded variable, and using such sigmoid function, for example, cannot estimate or deal this components in the time series, and therefore it's better to remove the trend from the series. Alternatively, or in contradictory to this result, the authors Sven Krohn and Nicolas Corenses, in their paper Forecasting Seasonal Time Series with Multi-Layer Perceptions, they criticize that when forecasting deterministic or stochastic seasonality, theoretically, they require different modeling approach, which has been ignored in neural network literature. Two authors actually explained that instead of taking, for example, or removing the seasonality from the data, or taking the past lag value, so the autoregressive model in the input layer, try actually to take some explanatory variables which explain those components into the neural network approach, and therefore will be better instead of just removing it. And from their empirical results, when estimating, so when the time series has deterministic seasonality, there is no need to make a deseasonalization. While Bruce Curry, on his paper Neural Networks and Seasonality, Some Technical Considerations, considers two aspects of the theory related to feed-forward logistic networks. In the first aspect is that, according to the author, the serious risk, so there is a serious risk of specification error when time series has seasonality. He gave some theoretical theoretical part. So both two aspects are based on some theoretical part and some empirical results. Why there is the serious risk? Because if the data has a seasonality and you only take, this actually is related once again with the first paper showed from Jean. They have only taken the past lag value of the same observation for their data that they have simulated and the real data that they have. And according to the author, it should be to put more attention to what kind of seasonality you have. Should only be using the autoregressive method into input layer, or should we include other approach, like for example some explanatory variable? Therefore, researchers only are attending only taking some autoregressive method, making some serious risk of specification error on the input layer. And the second aspect is that there is a need to reconsider the property of universal approximation in the context of seasonal variation. This is actually based as well in some theoretical results and empirical results that he made. Because why there is a need for the kind of to reconsider the property of universal approximation is that this is based on some very well-known paper of Barons in 1993. So the paper of universal approximation bounds for superposition of a sigmoidal function, where the author Barons tries kind of to use the Fourier representation to describe smoothness property for the neural network with only one hidden layer. And the results basically is that if the time series has seasonality, and this seasonality can be represented from a Fourier series, in this case there is a really need for a really high number of hidden nodes in order to estimate or capture this seasonality. And Bruce Curry, on his result, kind of justifies the idea of deseasonalizing or removing the seasonality from the neural network, because it makes the neural network model more parsimonious, but as well gives an attention to the researchers that in terms of time series having the seasonality, put more attention to how to better model the seasonality in terms of the input variable. Therefore, until now, most of the methods that I have found from the neural network approaches to forecast time series with trend and seasonal components are using the lag values of the same observation in the input layer, or using this input vector specification where you use some explanatory variable, not just the lag values. Later, there is as well the neural network with decomposition method, meaning that you decompose the data into the trend and seasonality, remove them, and then train the neural network in the preprocessed data. And the hybrid approach, or methodology, where Jean proposed a combination between the ARIMA models and the feed-forward neural network, where the forecast value will be kind of composed into the linear part, so the values forecasted from the ARIMA, so model and forecasted from the ARIMA model, and the nonlinear part model and forecasted from the neural network. In this behalf, our research was to consider both the traditional forecasting models and new approaches with respect to artificial neural network to forecast a really important factor in the private health insurance sector, the triggering factor. And the reason why we did such a research is that the private health insurance contract usually contain no time limit. Moreover, there is no right to terminate the contracts or reduce the insurance cover. To be able to provide such a lifetime guarantee for the insurance company, it is given that they can change the premium or adjust the premium in the event of a general increase in overall expected insurance benefits for the relevant tariff. This calculation is done annually and is known as the triggering factor, where the triggering factor is just a linear extrapolation of the total claim portion of the past 3 years. In this case, it is important for the risk management to have this predicted value as early as possible, and furthermore to give appropriate premiums in the future. In this case, our research was based to model and forecast the triggering factor using time series forecasting models and artificial neural network approaches, such as, for example, the regression model, ARIMA model, and use the best forecasting method found from the traditional one with respect to artificial neural network. So using the hybrid approach, and the other one is that using the decomposition method. So decompose the time series, remove the trend and seasonality, and train the neural network. The tariff that we have used is the private comprehensive health insurance tariff, quite important, which is divided, actually, this tariff is divided into male and female. And we had 4 real data sets. Monthly values started from 2004 till 2018. For example, the triggering factor is obtained by taking the loss ratio, so for the male, over the calculated losses of male for the past 3 years of observation. And in this case, to obtain the triggering factor, we had first to forecast all 4 data and then give the triggering factor for the company. For the application of neural network, we apply 3 types of data pre-processing. We adjust the trend, meaning that we remove the trend and we train with neural network. We remove the seasonality and train the neural network. The seasonality and trend were estimated by using the X11 method for the trend component, while the X13 ARIMA sees for the seasonality. Or removing both of them. So remove trend and seasonal components and then train the neural network. In the end, with respect to the decomposition method, the neural network, we had 4 types of models. So we had neural network which were trained on the original data, detrended, deseasonalized, and deseasonalized and detrended data. While from the traditional or from the linear models, the regression model, ARIMA method, and dynamic regression were built only on the original data. The best one found were selected in the hybrid approach with respect to neural network to determine the best neural network structure for each time series. The basic cross-validation method is used, where the data were separated in training, validation, and test set. Test set was the last 12 monthly values. The hidden nodes varies from 2 to 14. The partial autocorrelation function was used to find the past lagged value for the input layer. And one step ahead forecasting was selected for the model estimation and selection, while a multi-step ahead forecasting in iterative or recursive approach for the test set. We have used the sigmoid activation function on the hidden layer and the identity for the output node with a maximum training epoch of 1000. To compare all the forecasting methods, the 3 forecasting measures were used. So the root mean square of the research design was kind of lesson before, but basically we used again the cross-validation method for the neural network, and the methods that will be forecasting the triggering factor are compared by using the forecasting measures such as root mean squared error, mean absolute percentage error, and mean absolute error. So now the numerical results. In the first table, we show the results for the loss ratio values of male, where we only have first the models from the artificial neural network, and the traditional one, or the linear models such as ARIMA, regression, and dynamic regression, which are modeled into the original data. And looking now the testing results, we can see that the neural network actually fails to give better result than ARIMA model or the dynamic regression, so compared to the linear model, while a combination between regression methods and ARIMA method proved to be a very good approach, and in this case giving a lower forecasting error. And compared to the neural network approach, the dynamic regression, so artificial neural network trained on the original data, the dynamic regression method is giving the best forecasting results. Sorry. While the second table once again gives the results for the loss ratio values of male. But now we have the hybrid methodology and the neural network with respect to decomposition method. In the hybrid approach, we have all best forecasting methods from the linear model and the artificial neural network. And looking now the testing results and compare with the loss table, we see that each of the hybrid approach actually gives the best, so kind of the forecasting values is better, and is better, and actually compared to the ones only on the original data, trained only on the original data, combining both the artificial neural network and linear models is proved to be the best case in this case. And while the neural network trained on deseasonalized and detrended data, so with respect to decomposition methods, so those three other models are the decomposition method. And the one which gives the best forecasting accuracy, and therefore outperforms each of the methods here in the second table, and the first one is the neural network trained on deseasonalized and detrended data. The same results we get for the loss ratio values of male, where the neural network still fails kind of to give better forecasting results than the traditional one, and the dynamic regression method being as the best one for the loss ratio values of female, while the second table gives once again for the hybrid methodology and the neural network with a decomposition method, where for the loss ratio values of female, the hybrid methodology between the neural network and ARIMA model proved to be the best one, and therefore has been chosen to forecast or to obtain the triggering factor. In a similar fashion, we have used all the methods that were presented previously in the 4 tables for the loss ratios of male and female, again for the calculated losses. And among the best one from the linear model was the dynamic regression approach. And here in the first picture, we have the forecasted values, so the actual and predicted value for some years for the loss ratio, so for the calculated losses values of male, while the best approach with respect to neural network was detrending, so removing the trend and then training the neural network for the calculated losses values of male. While for the female, again, the same results, dynamic regression method proved to be the best one, and I just only showed some actual and predicted value for some years, while the approach with respect to detrending the data and training with neural network proved to be the best one. In the end, after having both forecasted value for the loss ratio of male and female and calculated losses, we now try to give the triggering factor and give some information to the private health insurance company, especially for this private comprehensive health insurance tariff. We took the true values for some years, so for 2015 till 2018. This table shows for the male customers. We have the true value of the triggering factors, and model 1 is basically the model of the dynamic regression method that was presented as the best one for the loss ratio and calculated losses, while the model 2 is the new approaches with respect to the neural network, and where the loss ratio was obtained or forecasted using the neural network trained with deseasonalized and detrended data, while calculated losses were obtained by adjusting the trend, removing the trend, and training the neural network. The absolute error gives on this column gives the absolute error between true value of the triggering factor and model 1, while the loss column gives the absolute error between model 2 and the true values. In general, we have found that kind of the model 1, the dynamic regression method, gives lower absolute error than model 2, so new approaches with respect to neural network. But however, for the private health insurance company, it was important to know whether the triggering factor was out of some interval or not. If that interval actually, if for example the triggering factor goes out of this interval, then the adjustment of the premium is made. And it was important to show that both model 1 and model 2 gave the same information whether the triggering factor will go out of the interval or not. So the loss table gives a comparison again of the triggering factors for the female customers, being the model 1 from the dynamic regression method and the model 2 being from the new approaches with respect to the neural network found as the best forecasting method. The triggering factor, which I said that if it stays within an interval, there is no adjustment of the premium. If it goes out, then adjustment should be made. As well, for the female customers, we have found that kind of the model 1 gives a better result, but of course the indication was that both model gave the same information to the company, which was important to know. And it was important to know which one, or if using both of them for the future values. In the conclusion, overall, our study shows that modern approaches from the area of neural networks are very, very attractive methods for predicting the triggering factor if they are trained and validated on trend and seasonal adjusted data. The hybrid approaches that combine neural networks with classic linear prediction methods such as the regression method or ARIMA models improve the forecasting performance of the respective traditional methods. Furthermore, rarely investigated variances such as linear regression with ARIMA errors are often superior to popular traditional time series models. Another finding of our research is that a naive application of neural networks to data that show a slightly trend and strong seasonality usually leads to worse results than an application of a simple time series models. Furthermore, data pre-processing that eliminates obvious effects can be viewed as an analog of using variance reduction methods in Monte Carlo method. There does not seem to be a uniformly best prediction method for the triggering factor over the years. However, it is advisable for the health insurance company in this case to use more than one forecasting method. And in the end, different architectures of neural networks, such as recurrent neural networks or the search for an optimal hyperparameter tuning of neural networks applied to forecasting triggering factors of health insurance tariffs can be made. So this concludes my talk. Here I show only some of the references. Our paper is actually available online for the audience. Thank you for your attention, and now I will be happy to answer any question or comments that you may have. And sorry for this inconvenience time that happened in between the talk. Thank you.
No need to be sorry. So thanks a lot, Fatlinda. Other questions? I think what you showed is a clear message. In no of your examples, detrending or deseasonalization actually had a bad effect, right? When you combine it with neural networks.
Yes.
Yeah. So I'm therefore quite surprised that people still think that that you should not need that, because I cannot imagine about, say, a reasonable detrending or deseasonalization method that makes the data worse. So from my side, I think that's a clear recommendation that you are giving. And it would be interesting if there is an opposing opinion about that. So, any kind of question? If still not, then I really recommend to read this article, because it's in German, so you can even learn German if you translate it. And I think, but the mathematics is of course international. So, if there is no question, then we make another 5 minutes break and then continue with Simon's talk. Thanks.